So in this video, we are now going to take that second term, right, this RT, all these natural log terms, and combine this into something useful. Not useful, but something a little bit easier to follow, and a form that you are going to be familiar with once you see it. Okay, so first, the RTs are going to be in front of everything. That's fine. Let's just look at what is inside of the parentheses here. So we have a bunch of natural log terms that are being added together and subtracted from each other. Now we can use some properties of natural logarithms to simplify this into something that we can follow a little easier. Right, so first of all, we have terms like this, nu y natural log of py over p naught. So we can use the properties of natural logarithms to say, well, this is the same as raising what's inside the natural log to that power. So we can say natural log of py over p naught raised to the nu y, the stoichiometric coefficient, those are the same. Right, so we can make that change first of all for all of the terms that we have. The other thing we can remember is that if you have another property of natural logarithms is that if you have a natural log of, let's say, x plus the natural log of y, that's the same thing as the natural log of x times y together. This is a property of natural logarithms. And similarly, if you have a subtraction instead of an addition, then they're divided. Now, subtraction instead of addition, they're divided inside of the natural log. So we can use both those properties together to say, okay, let's look at this big blue term up here. We'll have RT in front of everything, and it'll be multiplied by, RT natural log of, and now we can combine everything. We'll have in the numerator, we'll have a py over p naught raised to the nu y, multiplied by a pz over p naught raised to the nu z, divided by, because they're subtracted here, right, we have negative signs for the reactants, we'll have pa over p naught raised to the nu a, and pb over p naught raised to the nu b. All right, and so that is this blue term can be combined into this one single entity. And maybe this is starting to look familiar now. This is starting to look like an equilibrium constant, right? We have products, right? The pressure of the products in the numerator divided by a standard pressure raised to a stoichiometric coefficient, just like you do in an equilibrium constant. And the reactants are in the denominator, raised to their stoichiometric coefficients. And we are basically at the point where we've derived this expression that relates to equilibrium constants. Now, we go ahead and take this whole thing in here, and we define this as Q, which we call the reaction quotient. A quotient because it is a division that's happening and involves your reaction. Okay, so let's take this whole thing, this mess of an equation here in the red and blue, and let's write it out now that we've done these definitions. So we have delta G, the change in delta G for our reaction, which remember is how does G change with extent of reaction, is equal to delta G naught plus RT natural log of Q. Now that's hiding a bunch of stuff, right? Like it has we've taken all those other terms and defined new things to do this. Okay, so just as and again to remind, this is the change in Gibbs energy, under standard conditions, which for gases means that P equals 1 bar. That is the accepted definition of standard, and we have RT natural log of Q. Again, where Q, just to reiterate, this is defined as py over p naught raised to the nu y, pz over p naught raised to the nu z, divided by pa over p naught raised to the nu a, and pb over p naught raised to the nu b. Okay, so now you may be wondering, how would we actually use this equation? Now, this term here, this is a constant, And we can find the value for delta GR naught by using standard Gibbs energy of formations. So just like you would do for enthalpies of formation or absolute entropies, right? Delta GR naught is equal to our stoichiometric coefficients, right? Nu y times delta G of formation, make it a G, of compound y, and then we would, add, I'm going to give myself some more space here. We would add delta G of stoichiometric coefficient, mu z, delta G of formation of z minus our reactants, right? Nu a, delta G of formation of a, and all these are standard delta G's of formation, of course. And how you get these values is you would, of course, just look them up in a thermodynamic table. So calculating delta G naught is straightforward, right? This is something that you can do, and it's really straightforward to do. So in the next video, we will take a look at, and you've probably seen this before as well, I just mentioned. In the next video, we'll take a look at actually thinking about equilibrium and going from reaction quotient Q to equilibrium constant K, which you are familiar with.